Hi, my name is Azhar, and I'm part of the Fatigue Laboratory here at Texas Tech University. And today, I'll be talking to you about multifunctional, iron-doped, molybdenum HZSM-5 catalyst for methane dehydroaromatization. Some of the content that I'll be going over is I'll give you some of the background of the industry. We'll talk about the impact that this research can have, as well as what methane dehydroaromatization is, we'll also talk about the way we synthesize this catalyst in our lab, as well as how we measure catalyst activity. If you've ever driven past West Texas, you've seen a site familiar to the one in Figure 1. Essentially, what's happening here is methane is being flared in an oil and gas refinery. Now, methane is the primary hydrocarbon component of natural gas. It is a secondary byproduct of oil and gas operations, and it's often flared to the environment because its buildup can lead to explosions. In fact, in 2017, the Environmental Protection Agency reported that over 5.4 million tons of methane were emitted into the atmosphere from oil and gas operations alone. Methane can also be used as a building block to convert it to more useful aromatic hydrocarbons, such as benzene. That's going to be the focus of my research. So essentially, what we're trying to do is we're trying to convert methane to benzene using a one-step process. In industry, on a small scale, a two-step process currently is used. However, that requires the transport of methane to a different facility to treat it and convert it to benzene. And this is highly dangerous because methane is a gas and it's extremely hard to transport it. So there's additional costs associated with this process. The goal of my research is to develop a catalyst that can directly convert methane to benzene and have this catalyst have commercial grade applications. Essentially, what we're trying to do is we're trying to develop a catalyst that we can, instead of transporting methane, we can take this catalyst to wherever methane is being produced, such as these oil and gas refineries, and we can convert it to benzene by just reacting it with this catalyst. So some of the impact that this research can have is that methane is a greenhouse gas, and it's about 25 times as more potent than carbon dioxide. The amount of methane in our atmosphere has been increasing since the 1980s, and this can be attributed to higher productions of oil and gas operations, which lead to more of methane being fired to the environment. In fact, the Carbon Coalition Group attributes about 40% of the human-caused warming that the Earth has experienced to date to methane emissions. With 2017 and 2018 had some of the highest rates of increase in methane in our atmosphere at about 10 parts per billion since the early 2000s. Along with this, the amount of methane and carbon dioxide in our atmosphere is going to lead us to about a 3 to 4 degree increase in mean global surface temperature by the year 2100, and this is much higher than the Paris Climate Accords objective of keeping it to well below 2 degrees Celsius. Some of the economic impacts of converting this methane to benzene is that the United States actually currently imports most of its benzene, and these are estimated to be at a value of about $1 billion in 2019. Our production is only about 300 million, so currently there is a deficit which can be reduced by this conversion. Additionally, there is an increase in demand globally for benzene. As you can see over here, highlighted in green are the Asian and Australian continents, which are experiencing high growth rates for benzene. So we can, if we are able to successfully convert this methane to benzene, we can actually have an additional source of revenue for the United States by selling to other countries. So methane dehydroaromatization, or MDA, it's a one-step process that can convert methane to hydrogen and benzene using molybdenum zeolite-based catalysts. Essentially what happens here is we have 6 molecules of methane, which get converted to benzene, and 9 molecules of hydrogen. This process, however, has 2 challenges. The reaction is thermodynamically limited and has low conversion, as well as the catalysts suffer from rapid coking. Here in figure 4 is just a visual representation of what's going on inside our catalyst. We have our methane coming in and benzene going out. Speaking a little bit more about the structure of these catalysts, so zeolites consist of channels and rings and sinusoidal channels. They're about 5.5 angstrom in diameter, and so they're porous. So this is a visual representation of what they would look like. Specifically looking at one of these rings, we see that it's made up of a lot of silicon and hydrogen atoms. And a few of these will be silicon atoms will be replaced with aluminum. This creates the presence of a Bronsted acid site, essentially our proton donor, which will be used in our reaction. Additionally, we also have the presence of a metal, and that's going to be used for our catalyst activation step. So the reaction suffers from what's called product shape selectivity, in the sense that this methane actually gets converted to a bunch of different products. However, we are only able to collect benzene, which is our desired product. All the other products, such as naphthalene, toluene, they all get stuck inside these pores of the catalyst because the pores are only in 5.5 angst in diameter, and these molecules have diameters that are larger than that. So they get stuck inside these pores. This leads to our catalyst being deactivated. To give you a little bit more insight onto what's actually happening on the surface of the catalyst, here is our reaction mechanism, and in gray over here, this is the surface of our catalyst. So in our induction step, methane actually reacts with our metal, our molybdenum oxide, to form what's called molybdenum carbide, and it's a metallic carbide, and this is what actually helps our reaction takes place. So this is a very critical step in the formation, that it's the formation of our metallic carbide. This methane then reacts with this molybdenum carbide to form carbon's 2 species. The carbon 2 species will then go on and react with the Bronsted acid sites to form benzene, toluene, naphthalene. As I previously mentioned, we're able to collect this benzene. However, the naphthalene and toluene get stuck into the pores of our catalyst, and this leads to our deactivation. Essentially, these carbon deposits get stuck and they sort of clog the pores of our catalyst, and so our catalyst either has to be regenerated or replaced. So our lab has hypothesized that the most important step is the formation of a metallic carbide. So we've been trying to add a second metal and see its effects on the stability of our catalyst. So in figure 7, we have some past results of our lab, and these results are published. And here, essentially what we did is we added iron 3 using incipient wetness impregnation. And if you can see with the lines in red over here, by adding a second metal, we observed that there was greater stability in our catalyst over a period of time, as well as a higher overall benzene yield at about 7%. And so my research is focusing on how these metals are interacting. So some of the ways that we synthesize our catalyst is we use what's called incipient wetness impregnation. Essentially what we do here is we take our ammonium ZSM-5, our NH4 ZSM-5, and we subject it to pretty high temperatures. To get HZSM-5, we essentially evaporate the ammonia in this step, and that leads to the presence of our Bronsted acid site, essentially a proton donor, which is going to be our H. Next, we weigh out the amount of precursor or our first metal, and in this case, it's going to be the ammonium molybdate tetrahydrate to get the molybdenum onto our catalyst. And we calculate what's known as the incipient point of HZSM-5. So just going over the structure of HZSM-5 again, it's a porous substance. So the incipient point is the amount of water we can actually put onto the catalyst without it flooding. And so we calculate the amount of water and we add it to our precursor. Next, we impregnate the molybdenum solution and onto our catalyst a few drops at a time. Lastly, we leave it to air dry overnight and we set it in a furnace. Next, to add our second metal, we use what's called the ion exchange method. Here we weigh out the correct amount of our precursor, which is going to be iron 2 sulfate heptahydrate. We add this to about 50 milliliters of deionized water. We take our previously prepared sample of molybdenum HZSM-5. We put these together in an autoclave and we leave it in the oven at 180 degrees for about 18 to 20 hours. And here's just an illustration of this process. So once our catalyst is formed, we analyze to see the properties of our catalyst. We do what's called a BET analysis. This analysis helps us to understand the surface area, the micropore volume, the micropore area, as well as the external surface area of our sample. If you look to the figure onto the right here, here we have the surface of our catalyst. We essentially absorb a gas onto the surface. It's usually nitrogen. And what nitrogen does is it begins to start filling these pores. And this leads to the formation of a monolayer. And this process continues on until all the pores are completely filled. At this point, the reverse of this process happens, so the gas is now desorbed. So the nitrogen is removed away from these pores, and essentially what we get are two isotherms, which enable us to understand the surface area, the volume. So this analysis helps us to compare how different loadings of our metal with the zeolite affect the textural properties of the catalyst. To put it in simpler terms is how much of a metal we need to load on before our metal doesn't go to the positions we want it to and instead just starts to clog our catalyst. Next, we do what's called inductively coupled plasma, or an ICP analysis. It's a chemical analysis method that is used to identify the amounts and concentrations of all the elements within a sample. Here, this helps us understand how much of this metal we are able to successfully load onto the catalyst. Our synthesis of the catalyst does involve high temperatures, and so at times, some of the metals that we are trying to put into the catalyst actually evaporate or volatilize. So an ICP analysis is to compare the actual loadings from what we expect. So we can start off maybe saying weighing out 3.5 grams, but have noticed that only about a gram made it onto the actual catalyst. So the ICP analysis helps us understand how much of this metal we're able to load. Next, to measure catalyst activity, we run it through our reactor. Here's a little visual representation of what our reactor looks like. So we have these feed streams with gases and methane that go into our reactor. It's a packed bed reactor, and our catalyst is in the middle over here, and we subject the stream to pretty high temperatures. And we take our product stream and it goes past a gas chromatograph to understand the selectivity of our product, to understand the stability of our catalyst, as well as to understand how much of benzene we're actually able to obtain. So some of the preliminary results from my research. So here we've compared molybdenum loadings and iron loadings using incipient wetness impregnation. And we see that it didn't really affect it. So the line in red over here is just molybdenum adding a second metal, iron, using incipient wetness impregnation. We didn't really observe too many improved results. And the same goes for adding iron in other, or using iron 3 as well. However, using a different amount of iron, so using iron 2, so it has a lower oxidation state, actually led to improvements of our benzene yield as well as stability, and that's indicated by these black squares over here. So some of the problems that were associated is that we weren't able to control the actual location of our iron, and we weren't able to control how the two metals were interacting with one another. So some of the next steps that we'll be taking in my research is that we're going to reverse the order of incorporation of the metals onto the HZSM-5. So up until now, we've been using molybdenum HZSM-5 and incorporating iron onto it. What we're going to do now is we're going to take our iron and then first impregnate that onto our HZSM-5, then add the molybdenum to get our final catalyst. And we'll be using the ion exchange method to add the iron, as well as the incipient wetness or ion exchange method to add the molybdenum. Lastly, we'll be measuring the activity of our catalyst and comparing it with past results, with the hope that it's going to lead to higher yield of benzene and stability for our catalyst. These are some of the references that I've used to create this presentation. Lastly, I'd like to thank the Honors College Undergraduate Research Scholars Program supported by the CH and Helen Jones Foundations, as well as my mentor, Dr. Shima Khatib, for her continued support of my research. Thank you very much.